University Technology Malaysia, and he has also achieved his PhD from University Putra Malaysia, and he was in the top 2% scientist among world in the year of 2019, 2020, and 2021 by Stanford University. He has published, author or co-author more than 422 publications. Over to you, Dr. Ilyas, please.
Okay, thank you. Right, thank you. Thank you very much for inviting me to give as a presenter for this conference. So my name is Rushdan. So you can call, or in the Google Scholar you can type R.A. Ilyas. So for this evening, I would like to present my title on lignocellulosic fiber, reinforced thermoplastic starch TPS biocomposite. I'm from the Technology Malaysia. So this is my presentation outline, starting with a problem statement, and then starch packaging, natural fiber, nanocellulose, and then prime characteristic of the nanocellulose, sugar palm nanocellulose, reinforced sugar palm starch, application of a nanocellulose in food packaging, conclusion and reference. All right, so one question before I start the presentation. If one bottle of the water is thrown into sea, how long would it take to fully decompose? So it will take 450 to 1,000 years to decompose. So the plastic industry use a petroleum-based. Currently, the plastic industry use a petroleum-based synthetic polymer. So this one is a mountain of the plastic bag. Plastic bag was thrown in the landfill, and then the problem encountered is this plastic is a non-degradable and non-renewable in nature. So in this figure shows that don't trash where they splash, because this turtle might think that the plastic is a jellyfish. So the plastic bag are treated to the sea creatures such as a turtle. And then this one is sperm whale died because of the plastic. Right? And then whales died in Thailand after swallowing 80 plastic bags. And then how to overcome this problem is one of the method is we change the synthetic based plastic or the petroleum based plastic to starch biopolymer due to its availability and biodegradability and renewability. So the starch-based film for packaging has been reported to have a low water barrier resistant. So although starch can be one of the solution for the degradation of these synthetic plastic, however, they have a problem or drawbacks with the starch-based film. First one is the low water barrier resistant, and the second one is the poor mechanical strength. Right. So in order to improve these drawbacks, so we include the lignocellulosic fiber, or in the nanoscale, we call it a nanocellulose fiber. Right. So this component of the biocomposite. It can be combination of the fibers and the polymer. And then natural fiber. So we know that natural fiber we can get from any source, such as plants and animals. So, however, for this presentation, I will focus on the lignocellulosic. So, lignocellulosic fiber we can get from the two sources, non-wood of biofiber, and the one is the wood of biofiber. So, wood of biofiber is consists of recycled and softwood and hardwood. Right? So, another one is the non-wood of a biofiber, which are trunks, straw, bast, leaf, seed, and grass. Okay, this is some of example natural source fiber in Malaysia, such as sugar palm, coconut, cocoa pod husk. We have a bitter nut, sugar cane bagas, banana, pineapple, oil palm, roselle. So all these fiber, they can be reinforced with the starch to improve the mechanical and water barrier properties. Right. So we go to the nanoscale. So nanoscale of the natural fiber is a nanocellulose. It can be also a nanolignin. Right. For this presentation, I will focus on the nanocellulose. So nanocellulose has a nanostructure of 1 to 100 nanometer in diameter and 10 to 100 of nanometer in length. So it called a nanofiber instead of all right. Okay. So this is how we the nanocellulose, okay, from the sugar palm tree, and then we extract the fiber, and then from the cell wall of the fiber we extract the cellulose, and then from the cellulose we can extract the nanocellulose. Right. So this is the method how to extract nanocellulose from the lignocellulosic, or we call it plant fiber. So we can use a pretreatment, use a chemical and enzymatic or biological or physical method. Right. So for example, we can use a soda pulping, acid and alkali pretreatment, and then the cellulose isolation. So lignin was removed by using the sodium chloride, and then the hemicellulose was removed by using the sodium hydroxide. And then after that, we get cellulose. We can extract the nanocellulose using the chemical and the mechanical treatment. So some of the example, acid hydrolysis. So this one is an acid treatment. For the mechanical treatment, we can use a high pressurized homogenizer, ultrasonification, microfluidization, grinding, and cryo crushing. So this one I published in several journals regarding this method to extract the cellulose. Right. So this one is a primary characteristic of the nanocellulose. So currently we have 3 types of the nanocellulose. However, from the plants, we have 2, nanofibril and nanocrystalline. So what is the difference between nanofibril and nanocrystalline? It's the size, the size of the fiber, nanofibril. You can look at the length. The length for the nanofibrillated is below 1 micrometer, 10 micrometer. However, for the nanocrystalline, the size of the fiber, the length of the fiber is almost up to 100 nanometer. So there is a difference between the nanofibrillated and nanocrystalline. So you can imagine the shape of the nanofibrillated and the nanocrystalline. Crystalline it looks like a rice-like. However, for the nanofibrillated cellulose, it's a noodle-like. So this is the TEM and the AFM figures of the nanocrystalline. So it is like a rice-like. Basmati rice. All right, we can see that the diameter of the nanocrystalline is up to 9 nanometer, right? And then the length is up to 130 nanometer. So for the nanofibrillated cellulose, because the length can be up to 10 micrometer, we only look for the diameter of the nanofibrillated cellulose, which is a 5.5 nanometer. So this one is a bacterial nanocellulose started from the bacteria. And then this some of the properties of the nanocellulose that why we should reinforce it with the starch. So first is the high surface area, high aspect ratio, high crystallinity. So low density, high mechanical strength, high tensile. It's a renewable and availability as long as it is plant, and you can extract the cellulose from it. It's a biodegradability, it's a biocompatible, high thermal stability, and besides that, it has an abundant surface of the hydroxyl group, which this one we can modify to be reinforced with other polymer, and it's a less toxicity. Okay, this is the type of the nanocellulose that have been extracted by our team. So this one is a ginkgo cellulose. And then the water hyacinth cellulose, and then the kenaf cellulose, sugarcane bagas nanocellulose, agave gigante nanocellulose. Right. So this one is the out of scope, but still this bacterial nanocellulose can be reinforced with the starch to increase the mechanical properties. So this one is the project for the sugar palm nanocellulose, in which we extract the nanocellulose as well as the starch from the same tree. Right. This one is the starch. This bioplastic starch, thermoplastic, can be used for the food packaging. Okay, sugar palm starch, sugar palm from the sugar palm fiber can extract, can become a cellulose. After that, isolate the nanocellulose using the chemical treatment. We get the nanocrystalline cellulose, and the mechanical treatment we can get the nanofibrated cellulose. So this one is the sugar palm nanocellulose reinforced with the sugar palm starch. So we can see that when we reinforce the nanocellulose, nanocrystalline cellulose, we can get only 0.5. The tensile strength is increased up to 11.747 megapascal, compared to the raw starch, which is the 4.8 megapascal. So they increase up to double. And then beside that, we can also see that water vapor permeability, in which when we include the nanocellulose, the water vapor permeability is decreasing. Means that it improves the water resistance. Okay. And then beside that, nanofibrated cellulose. So these are different between the nanofibrated and nanocrystalline. So we include 0.5 for the nanocrystalline. However, for the nanofibrated cellulose, we have to include 1.0. So why is it different? It's because of the surface area of the nanocellulose. Okay, so besides that, it also improves the oxygen barrier properties of the nanocellulose due to the torches theory. Right, when we include the fiber on nanocellulose, we can see that there is the water, the air need to go through the torches or the barrier, right? Okay, so this is a different. So when we include, so the research was done in 2012. Then when we include reinforce the sugar palm fiber, which is raw sugar palm fiber, we see that the mechanical strength of the starch increase up to 5.5. And then we try to include with the cellulose 10.5. And then we include sugar palm nanocrystalline cellulose up to 11.47. And then sugar palm nanofibrated cellulose reinforced with the sugar palm starch increase up to 10.75. So however, if you see this one, it takes 30%. 30% of the natural fiber of the cellulose to get this tensile strength. However, when we include only 0.5%, we can get this type of strength. So, okay, so this research, it is really can be contributed to be used in the packaging application. And then another thing is, this one we also extend the research to reinforce with the PLA and the starch and nanocellulose. Right, this one published in the nanotechnology review. Besides that, we also encounter that after the mechanical strength increase.
Dr. Ilyas, I'm just interrupting you. Due to the shortage of time, you can continue for just 1 or 2 more minutes, and then so that we can.
Okay. So, however, when we see that the starch is being attacked by the antimicrobe, so what we do is we include the silver nanoparticle to make the starch antimicrobe. All right. Okay, as a conclusion, the reinforcement of the lignocellulosic fiber with the thermoplastic polymers improve the mechanical, air permeability, and water properties of the biocomposite. So these are some of the reference that I list this down. And then these are some of the recent book publication, the bio-based and nanocellulose, now and the biocomposite. Also the mineral field polymer composite, and the recycling of the plastic, advanced composite in aerospace, composite in the biomedical, and then pulping and additive manufacturing of the bio and the synthetic. All right, okay, so thank you. So that's all from me. Thank you. So you can contact me for further information. You can contact me at ahmadilyas@utm.my.
Okay, thank you, Dr. Ilyas, for this nice and informative talk. Let me see any question, if we have any question. If no, then thank you again, Dr. Ilyas. We will move to our
Alright.
next speaker,
Okay.
who is Abu Hassan Noordin. He is a lecturer in University Technology Malaysia, and he has already published 12 articles, and his area of expertise is polymers. So over to you, Dr. Abu Hassan. So sorry, I think Dr. Abu Hassan has some problem in his network connection. So we will move to the next speaker, which is Noor Farhana Binte Abdul Samad, and she is a PhD student in Faculty of Chemical Engineering Technology, University Technology Malaysia, and her area of expertise are nanocellulose, rubber-based membrane, and wastewater treatment.
Excuse me.
Sorry.
Do you mind if I share my screen, because the microphone from my laptop is not really well.
Okay. Is you Abu Hassan, Dr. Abu Hassan?
Yes.
Okay, so you can continue. If you have no problem with the connection, you can continue your presentation.
Can you see my slide? I've shared my screen. Hello?
Yes, Dr. Abu Hassan.
Do you see my slide right now?
Yes,
my
we
video?
can
Okay.
see. We can.
Assalamualaikum everyone. My name is Dr. Faculty of Chemical Engineering. So for today, I would like to present my topic, entitled review on the state of nanocellulose. Cellulose, one of the most valuable polymer on Earth, can be extracted from natural plants, food, agriculture residues.
Sorry, Dr. Abu Hassan. I think so. There is some issue with the sound quality. Yes, we can see your video, but the sound quality is not good, and we are unable to understand it properly. So, if you could manage something else, then we can continue. Otherwise, we will move to the next speaker, and when we will come back to you.
It's okay. I think I can present right now, but hopefully my speaker is okay. Wait a minute. Okay, how about now? Can you see my slide?
It's still the video slide which you are showing.
Okay. Sorry. How about now?
Yes, we can see your slide now.
Okay. Okay. Assalamualaikum and good day, everyone. My name is Abu Hassan Noordin from School of Chemical and Energy Engineering from Faculty of Engineering at University Technology Malaysia. So I would like to present my topic entitled A Review on the Application of Nanocellulose. So cellulose are one of the most abundant biopolymer on the earth. It can be extracted from natural plants, wood, agriculture residue, industrial waste, bacteria, and algae. Compare with cellulose, nanocellulose has much smaller diameter, typically less than 10 nanometer, that renders many unique properties. Among many others, this property includes with high mechanical strength, large surface area, and low visual light scattering. And then nanocellulose can be obtained by disintegration of plant cellulose pulp and by the action of specific type of bacteria. Once it is produced, nanocellulose can be used to make a transparent film, fiber, hydrogel, or aerosol, and that exhibit extraordinary mechanical, thermal, and optical properties. In this review, we focus on the application of nanocellulose, including in food packaging, wastewater treatment, biomedicine, and carbon dioxide capture. Okay, for food packaging, there has been an increase in demand for packaging materials which are non-petroleum based, biodegradable, which pose a minimal threat to environment and are manufactured from sustainable and renewable resources. For example, previous study has presented the need of biodegradable polymer to replace the petrol-based synthetic polymer as raw material for wrapping. Conventionally, used synthetic polymer have an edge over the biopolymer. Biopolymer have poor barrier, thermal and mechanical properties compared to their synthetic counterparts. This limits their usage in commercial applications such as food packaging. So recent years, there is increased attraction towards the nanotechnological application in packaging, and nanofiller or additive with their size lying in the range of 100 nanometer. These nanofiller are used in improving the properties of polymeric materials in a composite for desired application. Okay, such property of the film ensure that the packed food will last long. And then next is the application of nanocellulose in wastewater treatment. The massive amount of hydroxyl group on the nanocellulose surface allow for the establishment of interaction with heavy metals, organic compounds, and other pollutants. Besides that, nanocellulose may function as a membrane filter that take up microorganisms and other contaminants from polluted water. Similarly, the separation of metal like silver ion, copper ion from polluted water may be accomplished by mixing magnetic nanoparticle with cellulose polymeric matrix and using an external magnetic field. So through direct altering the nanocellulose surface via sulfonation, amination, and carboxylation, and adjusting key variable like pH, adsorption load, temperature, and agitation speed, it is possible to enhance the retention of this dangerous metal by adsorption from aqueous solution. So currently, a large number of businesses all around the world produce enormous amounts of nanocellulose from readily available lignocellulose materials at low cost, but advanced research study in adsorption must be carried out using real wastewater by using more potent adsorbent for scaling up the laboratory assays. Then next, the application of nanocellulose in drug delivery system. So nanocellulose can be used in drug delivery system to regulate drug release and interaction with target molecule, enhancing the efficiency of medication administration, to connect medications and non-ionic substance with a hydrophobic nature to the nanopolymer. Changes to the nanocellulose surface must be made. And then, for example, according to the recent study, cationic surfactant and mechanism of sulfonation, silation, esterification can be utilized to adjust the negative charge of nanocellulose, which increasing its hydrophobic character to promote interaction with pharmaceutical and manage its gradual release. And then this is the application of the nanocellulose for CO2 capture. So the incorporation of inorganic particle or chemical modification of nanocellulose are the two of the primary method for CO2 adsorption. These nanomaterials can be functionalized and used as adsorbent or as a component of membrane to selectively retain CO2. In this way, nanocellulose has been used to participate in chemical or physical cross-link hydrogen that may be frozen and dried to produce aerogel, such as those made from glutathione, borax, or epichlorohydrin. And then by modifying nanocellulose aerogel with silane, such as silane, CO2 can be collected through chemisorption mechanism, and then aerogel made of fabricated nanocellulose impregnated with suspension of crystalline nanocellulose that has been functionalized was proven to be used for physisorption based CO2 retention. So in conclusion, since nanocellulose is renewable, biocompatible, and biodegradable, it has many appealing applications. But for the laboratory scale research investigation are required to advance the usage of nanocellulose for environmentally friendly application and its commercial manufacture customized for various end user application. Okay, thank you.
Thank you, Dr. Abu Hassan, for your informative talk. We don't have any questions, so we can move to the next presentation. Our next speaker is Noor Farhana Binti Abdul Samad, and she is a PhD student in Faculty of Chemical and Engineering, Energy Engineering, University Technology, Malaysia. She has already published 5 articles, and she is going to talk about polymeric membranes for wastewater treatment applications. Over to you, Noor Farhana Abdul Samad.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to everybody. Hi, my name is Noor Farhana Binti Abdul Samad, and I'm supervised by Dr. Ahmad Ilyas bin Rushdan and Associate Professor Dr. Nurjita Betingadi. We are from Faculty of Chemical and Energy Engineering from University Technology Malaysia. Okay, today I want to share about a review entitled Polymeric Membrane for Wastewater Treatment Application. Okay, this is my presentation outline. Well, first introduction, then wastewater treatment system, membrane technology for water treatment application, then polymer membrane feasibility, and then polymer nanocomposite membrane for wastewater treatment, and conclusion. Okay. Most developing countries are confronted with the problem of water pollution, which is a key worry that must be addressed to ensure people's well-being. Water pollution occurs when there is a change in physical, chemical, and biological properties from its original state that exceeds the limit and standard set as contained in the water quality standard. Okay, in general, the pollution is caused by human activities that have adverse effects on the environment, such as health, living resources, ecological system, and others. One of the main causes of water pollution is due to a permanent source of wastewater from sewage treatment plants and industry. Therefore, effective and capable solutions to overcome this pollution problem are very much needed. So, various advanced treatment methods, including physical, chemical, and biological methods, have been used to treat wastewater from the industry. Among the methods that are often used are biocombustion, coagulation, flocculation, steam reforming, ultrasonication, membrane filtration, adsorption, or combination thereof. Okay, and then the wastewater treatment method using membrane technology are gaining attention because membrane are able to filter contaminated organic matter and then obtain and recycle clear water to the processing plant. Okay, this alternative method provide more efficient treatment method, which is require minimal energy and do not require the addition of chemical into the waste system. Thus, membrane separation technology is one of the potential technologies to treat industrial wastewater without disturbing the environmental balance, and the porous membrane have been widely used for water separation process. Okay. This table shows the advantages and disadvantages of different types of treatments studied by Yashni et al. 2020. From the table, we can see the membrane filtration advantages are high removal rates, energy efficiency, and high selectivity, easy handling, and cost efficiency, and can remove high rate of organic matter and reduce aeration. Okay, and then Generally, a membrane can be identified as a thin layer of semi-permeable material which separates substance and allows one part of a mixture to permeate the membrane while inhibiting the other when a driving force is employed. Up to now, there are 4 different pressure-driven membrane types used in water and wastewater treatment, namely microfiltration, ultrafiltration, nanofiltration, and reverse osmosis based on the membrane pore size and operating mechanism. However, despite decades of research and development, membrane filtration remains plagued by long-standing operational issues which is permeability and fouling. Okay, so some modification have been made to be the best membrane separation process. Okay, many membrane used in wastewater treatment, either commercial membrane, inorganic, polymeric and organic polymer composite, and then nanomaterial and hydrophilicity material. Okay, single polymeric membrane have gained popularity in water and wastewater treatment because of their filtration properties, good mechanical strength, chemical stability, and low cost. With this, single polymer membrane have advanced from conventional simple polymers such as cellulose acetate and polyamide to more complex material like polysulfone methylene, quaternary phosphonium hydroxide, polyfurfuryl alcohol, chitosan, and sulfonated polyaryl and other sulfate with improved permeability and selectivity characteristic. Okay, and then the other modification are by using fabrication method, which is by using molding, solution casting, sintering, stretching, coating, electrospinning method, and phase inversion. And then the modification have been made to the membrane material due to the properties of wastewater, which is oily, color, organic matter, and then textile, and then pharmaceutical waste, and then heavy metals. So, numerous studies have been devoted to development of antifouling membrane by improving membrane surface smoothness, charge, and hydrophilicity. Okay, this can be achieved by a selective material, polymer material, then modify the membrane surface properties. Hydrophilic polymers are preferred modifiers that can provide antifouling properties at lower cost and use of chemical. Okay, this is an example that use the polymer membrane that used in research study, which is they use ANR PVC microcrystalline cellulose by using solution blending technique. So the membrane can be reduced, the COD, BOD, and total suspended solid to 99.9%, 70.3%, and 19.9% respectively for POME treatment. And then by using polysulfonamide, polyacrylonitrile fibers, they use emulsion electrospinning. The membrane have outstanding thermal stability in air 400 degrees C, and then strong acid alkali resistant at the pH range from 1 to 13, and have robust tensile strength. And then the membrane have high water flux over 3,000 liter per meter square per hour, and oil rejection efficiency of 99.6% for breast oil in water emulsion for oily water treatment application. Okay, and then they use polysulfone by using phase inversion method, non-solvent induced, which is the membrane have a high water flux value with slightly higher solid rejection at 99%. Okay, by using polyether sulfone electrospun fibers, by using electrospinning method, the water permeation flux and oil rejection of the electron fibrous membrane in oily wastewater treatment are in the range of 54 to 620 and 39% to 81% respectively. And then by using PLA and PEG silica, by using phase inversion method, the biochemical oxygen demand and chemical oxygen demand and total suspended solid removed to 99.5%. And by using polyether sulfone, by using phase inversion, The COD, BOD, TSS reduced to 90.9%, 70.3%, and 19.9% respectively. Okay. So, this research attempt have focused on developing nanocomposite membrane for sustainable water purification, aimed at enhancing fouling resistance and surmounting the trade-off relationship between permeability and solid rejection among different nanocomposite. Polymer-based nanocomposite membrane have driven considerably attention in recent years. Generally, incorporation of nanomaterials into polymers can tune structure and physicochemical properties of membranes such as hydrophilicity, charge density, porosity, chemical, thermal, and mechanical stability. Unique functionalities such as antibacterial and photocatalytic characteristics can be introduced to the membrane by incorporation of nanomaterials into polymer. In addition, physical characteristics such as strength and modulus can be improved as a result of strong interfacial interaction between the nanoparticle and the surrounding of polymer matrix. Okay, nanofiller materials such as nanoclay, graphene oxide, carbon nanotube, cellulose, nanofiber, and nanocellulose have gained particular interest in the water treatment community due to unique properties like high surface area, low cost, fast absorption, kinetic, thermal stability, chemical stability, and mechanical stability. Okay. Okay, this is a polymeric nanocomposite membrane that used in water treatment application. So many types of nanomaterials that combine with the polymers with others, some various method for water application. Okay, as a conclusion, the membrane materials, shape, cross-section, and fabrication method have primarily attributed to the performance of the membranes. Then the utilization of some polymeric materials and preparation method of effective the permeability, selectivity, and rejection of membrane for wastewater treatment application. Okay, that's all from me. Thank you.
Thank you, Dr. Noor Farhana. We have one question for you from Dr. Asif. What non-solvent chemicals are used for delayed phase inversion in cellulose-based membranes? Noor Farhana, silent.
Okay, I'm here. So I will answer after this. It's okay?
Sorry, Noor Farhana, we have one question from Dr. Asif that what non-solvent chemicals are used for delayed phase inversion in cellulose-based membranes? Okay, I think so. Noor Farhana is not with us, so we can move to the next presentation, which is going to be presented by Siti Noor Hawanis Binte Hussain, and she's also a PhD student in Faculty of Chemical and Energy Engineering, University Technology, Malaysia, and she is going to present on a topic of a review on different pulping methods, chemical, mechanical, and chemi-mechanical pulping. So over to you, Siti Noor Hawanis. Miss Manis, we are waiting for you actually. Could you share your screen? Yeah, we can see your, okay. Now we can see your screen also.
Assalamualaikum and a very good day to all. So my name is Sina Harani from Spain, and I will be presenting about the review on different parking aspects, mechanical and semi-mechanical parking. So this is my presentation outline for today. First is for the introduction. I will start with the parking process overview, which involves of all parking process I will be talking about today. The next is chemical parking, and jump to the semi-chemical parking and mechanical parking. And last one is the conclusion. So for the introduction, paper industry plays a very important role in the world economy. Now we realize we use paper in the shopping mall, at the so we say the the pulp and paper industry has existed since the first century when the Chinese inventor in Thailand has invented the first satellite writing material. I believe he invented the paper-like materials with
Sorry, Miss Manis, we cannot see your screen anymore now.
I say one more time and can you see?
Okay, yes, we can see now. Yes, you can continue. We can see your screen now.
Okay. So I So I believe Thailand has invented the paper-like material with the he makes the textile fibers from the bark of the mulberry, and in the hello, doctor.
Yes, Miss Manis. Actually, I think so. I might.
Presenting. Sorry.
Sorry, I think so. There is some problem with your voice also, and also with your presentation. So, if you have our recorded video, could you send it to us so that we can play it in some later time?
Sorry, I don't have any recorded video. Just now the internet connection is doing well.
Okay, so you can continue from the where you left, and we will try last time, and otherwise then you can connect it again, and then we will give you time like after some speakers. You can give a last try.
Do you hear me here?
Yes, yes, we can see your screen and we can hear you also.
Sorry for inconvenience. So the pulping is the process of separating cellulose fibers from lignin by breaking the bond of living material. The first developed pulping process is the mechanical, which is the stone ground wood pulp process by German chemists. And then the evolution of the chemical method. Last of all is the chemical mechanical pulping process. So for the pulping process overview, I start with the mechanical pulping, which is three types of pulping. First is the stone ground wood pulp process, refiner mechanical pulp or RMP, and the third one is the thermomechanical process. So the chemical pulping consists of sulfide and the sulfate process. And mechanical pulping, I will cover about the NSFP, which is the neutral chemical process, and the cold soda. For the mechanical pulping, the pulping technique is produced by which the fibers are produced through the mechanical means. It consists of twisting, grinding to produce a part from the lignocellulosic material into the individual fibers. It is caused by physical means. The process preserves both lignin and the cellulose fibers, resulting in a paper yield of 90 to 98% per unit volume of wood with lower strength, softness, bulk, and brightness. The benefit of using the mechanical pulping is the high yield and the cost is lower. Less amount of fine is used, and the high OPEX product, which is broad fiber smooth surface paper. The stone ground pulping process is considered low cost. Produce paper with high absorbency. All this mechanical pulping of all involve the pressing of materials into a rotating grindstone with speed range from 1000 to 1200 revolutions per minute. The grindstone abrasion force will tear the wood into fine fibers, and the fiber fragment is continuously washed from the grindstone by a water sieve. The friction that develops in the grinding zone will raise the temperature, softening the wood and thus facilitating fiber separation. So this is where the heat will be produced softer lignin, and it will change. It will lower the damage of the fiber. The refiner mechanical part consists of threading grinding wood, and it is produced between rotating metal disc or plate. It was created in the 1950s to improve the paper quality. It consists of two stages, which is the first one involves the defibrillation of wood, and the second one involves the loosening the fiber structure in order to increase the flexibility of the fiber. And the benefit of this process is it produces stronger pulp, which is longer fiber, bulkier and darker than the stone ground wood process. And also various sources of wood can be used in this process. This process usually used to process softwood or hardwood. This is the basic flow diagram of the thermomechanical pulping process. The difference between the refiner mechanical process is this process will involve the use of heating, which is the steaming of the fibers before proceed to the blue cyclone. And I continue with the chemical pulping. The process involves dissolving and removing plastic from the. This is most widely used pulping method for producing high quality paper in the world. chemical pumping employs chemical for some resource delivery. The chemical pumping process is treating the wood chips with mechanical and aqueous solution at high temperature and pressure in order to remove the cellulose. So the chemical pumping produces half that of mechanical pulp method, which is half from the mechanical one. This is the overview process of sulfur pulping. For the sulfur pulping, the process relies on sulfur dioxide, which is an essential component. It involves working wood chip in a digester at high temperature and pressure with an aqueous solution of sulfur dioxide and calcium, sodium, magnesium, and the ammonium bisulfite. The sulfur process degrades wood by dissolving lignin and cleaving lignin bond via sulfonate function. The sulfur pulping is appropriate for wood species with low adhesive, which is tannin, polyphenol, lignin resin fat, as adhesive interfere with the pulping process. The yield produced from this process is quite similar to this kraft pulping process. Next one is the sulfate or kraft pulping. This process involves dissolving and removing the lignin matrix from the cellulose fiber, which is quite same as the latter one. The six cooking chemicals, what we put and which is the NaO and the nitrogen sulfide used in this process. This process usually need bleaching because to make the white pulp, as the pulp remains brown even after the after finish the process. The process will produce longer fiber, stronger paper, but the yield is quite low, which is only 50%. Semi-chemical pulping (NSFP). The process will use less chemical with the higher yield, which is the 65 to 80% of pulp. This is the process using based on wood material. It is poor bleachability, which is also the bleaching process. The main idea of this process is to make a mild coat among the fiber in order to separate them. The high yield offers reduced thin solution problem. The product is the liner board and the corrugating paper. So for the pulping, this is the treatment of wood chip with the sodium hydroxide solution process. The temperature is usually ranging from 20 to 30 degrees Celsius prior to this final defibrillation. It is frequently combined with the kraft process in order to achieve sodium hydroxide recovery. This process only takes 50 to 2 hours in order to impregnate the wood chip with the cooking before, which will cause the fiber swelling and it prevent the polyol loss. The pulp yield relatively high in this process. It is 85 to 92%. This is because the lignin degradation and the polyol dissolution are quite lower. The disadvantage of this process is it produces low brightness of paper. So this process also needs to be improved by bleaching with the peroxide hypochlorite. This is the recent advance in pulping process. First one is the chlorine-free bleaching, which is a byproduct that is harmful to the environment. PCF is the process of latest one, which is the oxygen-derived form, which is H2O, H2O2. The next one is the development of the organosoft pulsing. It is reduce. The function is to reduce the sulfur emission but produce high yield pulp and below residual content, high brightness and good size. Pulping of non-wood plant species is mostly made up of 44% straw material, 80% bagasse, 14% reed, 30% bamboo, and others is only 11%. The next one is the nanotechnology in pulp and paper making. This is quite new actually, maybe for me. Cellulose and lignocellulose have a great potential as nanomaterials and also abundantly renewable. Wide range of paper and packaging industries has already incorporated nanotechnology throughout the production system. So in conclusion, mechanical treatment can isolate the individual fibers in different way, but the chemical treatment can modify the chemistry of the paper surface itself. Self-pulping is a very complex process because time-consuming, chemical concentration, and very high pH. The temperature also can be modified resulting in cellulose fibers with different properties. Both kraft and sulfite pulping are integrated procedure where not only chemical treatment are performed, but also several mechanical steps are used to improve the even distribution of chemicals, and this is to get the better dispersion of fibers. So by adequately combining mechanical and chemical treatment throughout the production of cellulose fiber, desired properties can be imparted to the fiber. So this is some of my references. And that's all for me. Thank you.
Okay, thank you, Mr. Vanis, for your talk. We have one question for you. It's from Dr. Asif. How to reduce the charge on surface of cellulosic fiber after kraft treatment?
I cannot.
Could you able to listen my question?
Basic question.
Sorry, we are not able to listen you properly.
No, your voice is.
Okay, thank you. Thank you so much, Mr. Vanis.
Sorry?
Could you hear to us? Okay. Okay, so we will move to our next speaker, who is Adil Abbas. He is a MSc student in National Textile University, and he is going to present on the topic of influence of inlay and stacking sequence on flexural behavior of knitted reinforced smart composites. So over to you, Adil Abbas, please.
Sir, please confirm, am I audible?
Yes, yes, we can see your screen also, and we can listen to you also.
Assalamu alaikum. I am Adil Abbas, and today I am going to present on the topic of influence of inlay and stacking sequence on flexural behavior of knitted reinforced smart composites. And my research fellows are Muhammad Soeb Anas, Professor, and Mr. Zishan Azam. Here are the overall outlines that firstly we will have an introduction to the topic, then inspiration of research, then we will go through our materials and methods, and then results and discussion and conclusion. First of all, introduction composites are the macroscopic or microscopic combination of two or more different materials. Generally, the matrix and reinforcements are the two phases. In fibrous composites, we generally use fibers, yarns, and non-one materials as a reinforcing material. And our continuous phase is our epoxy or some other as per requirement. Then the second main aim of our research is the smart feature of composites, or it is also called as self-diagnostic properties. These are terms that as an ability of material to sense any of mechanical, thermal, or chemical changes in their structures. And these can be induced using intelligent devices, piezoelectric materials, and by nanomaterials. Actually, fiber reinforced composites are always an integral part of complex infrastructure, so their health and monitoring of their health is always necessary to keep the smooth ongoing of the system. For example, in an advanced Boeing, there is a 50% part of composites in boards and bridges and some more complex infrastructures. Composites are the integral part. So it is necessary that there should be some smart features or self-diagnostic abilities in composites to monitor their health in real time. There are some researches that use acoustic sensors, fiber grating sensors, and piezoelectric transducers to check the smartability of composites or induce self-diagnostic properties. But there isn't still any significant use of knitted reinforcements for self-diagnostic properties induction. Hence, this work will focus on developing knitted reinforcements to induce the self-diagnostic properties in composites for their structural health monitoring. Firstly, for reinforcement knitting, there was used a specialty knitting structure that used an inlay yarn and a base pattern. Carbon fiber being a conductive material was used as an inlay yarn as it is missing from the figure, and base knitting material was of polyester yarn, and the pattern was used as 3x1 and 6x1 inlay pattern, which we will further see in the slide. And for composite fabrication, there was a hand lap technique, and unsaturated polyester was used as a resin. Actually, there were two different inlay patterns and two different stacking sequences. So overall, there were 4 specimens, and in characterization, we have a electromechanical characterization using flagellal testing and electrical resistance measurement simultaneously. So we can see our composites behavior against mechanical loading in terms of electrical resistance. Here is a detailed view of our inlay pattern and stacking sequence. Firstly, we can see that there are composites having 3-layer stacking. First of all, of plain rib, then stimuli layer with carbon inlet, and then plain rib. And second figure indicates our stacking sequence of 4 layers, in which we have top and bottom plain layers, and there are stimuli layers in between the plain layers. After flagellal characterization, simultaneously seeing the mechanical and electrical resistance characteristics, we can see that with respect to test time, there is a linear increase in strain, flagellal strain, and electrical resistance is also fluctuating with respect to the strain. It can be seen that increasing strain has a positive impact on the electrical resistance, that the resistance is also increasing. And we can see that initially with cracks propagation, there is a small change, but after a major crack, there is exponential increase and the resistance goes up to a critical value. And when there is a strain hardening in composite, actually termed as the relocating of bonds, electrical resistance again decreases. And we can see from the graph that on critical resistance value, our composite has lost its health from the fractures indicated in the figure. So it is time to replace the composite. Then in the second specimen of 6x1 inlay and of single stimuli layer, we can see that there is initially small fluctuation area, and then there is exponential shift due to fibers cracking. And a critical electrical resistance values are difficult to identify in the 6x1 inlay pattern because there are less amount of conducting yarn used in 6x1 inlay pattern as compared to the 3x1. Similarly, if we compare electrical resistance values of both 3x1 and 6x1 inlay patterns, we can clearly see that the electrical resistance of 3x1 specimen is more linear as compared to the 6x1 specimen. As during the initial test time, there isn't any specific fluctuation in the electrical resistance, depicting that our 6x1 inlay pattern isn't capable to monitor the health of the composite. While in case of 3x1 inlay, the initial linear increase can be observed, that is showing that composite is more smart as compared to the 6x1 inlay. And also our 3x1 inlay composite is capable to sense its health during the strain hardening region, while for 6x1 inlay, there isn't any strain hardening region, and electrical resistance is abruptly stopped to the out of limit value. Similarly, changing the stacking sequence from 3 to 4 layers with double stimuli layer, we can see that there is a significant decrease in electrical resistance during initial mechanical loading, and this can be related to the decrease in electrical resistance of wires on bending, because the electrons with low velocity drift are capable to move through the bended wire, and electrical resistance is decreased, and same was the case with the carbon fiber. However, after a certain time, there was a abrupt increase in the electrical resistance, making it to the threshold value, and then there was a quadratic decrease in the electrical resistance due to the strain hardening, and then major fiber failure started, at which composite lost its health. Then similarly for 6 by 1 inlay pattern and double stimuli layer, we can see that there is only linear increase. There isn't any initial fluctuation or decrease in electrical resistance following the pattern of previously described single stimuli 6 by 1 composite. That 6 by 1 inlay pattern isn't capable to sense the composite health properly due to the less amount of carbon inlaid yarns. Then making an overall comparison of our 6 by 1 and 3 by 1 inlay composites in single and double stimuli layer, we can see from the first figure that there is a higher critical value in single stimuli layer that is replaced by a lower critical value in our double stimuli layer composites, while for the 6 by 1 inlay there is also a higher critical value of 1.6 kilo ohms, and it is replaced by a lower critical value in changing from stacking sequence from 3 to 4. From the results, we conclude that knitted reinforced smart composites are viable choice for structural health monitoring, and these can sense the mechanical changes in composites with respect to their electrical resistance, and making our inlay pattern dense, for example, changing from 6 by 1 to 3 by 1 inlay pattern and making the stacking sequence more dense. There is a linear increase in electrical resistance against mechanical damages. And for future perspectives, we can develop knitted reinforced composites with self-diagnostic function and have a sound-based alarming systems. And practically, these can be integrated into the running systems to check their reliability. Here are the references. Thank you. Questions?
Thank you, Mr. Adil, for your nice talk. We don't have any questions, so we can move to the next presentation, who is going to be presented by Dr. Mohammad Tosif Khabar. He has done his PhD from in textile science and technology from University of Leeds, I think so. Okay, so he's going to present today on the topic of electrospinning process optimization of chitosan nanofibers production. So we are going to start the video from Mr. Dr. Mohammad Tosif.
Hi, good afternoon. My name is Dr. Mohammad Tosif Khawar. I'm working as an assistant professor in Department of Clothing, School of Engineering and Technology, National Textile University, Faisalabad. In this short presentation, I'm going to highlight the key finding of research based on process optimization of chitosan nanofibers production. Chitosan is an abundantly occurring amino polysaccharide of cationic nature. Chitosan is based on chitin. Both chitin and chitosan are found abundant in nature from a number of natural renewable resources. The main source of chitin are skeletal materials of sea creature, including crabs, prawns, lobsters, and shrimps. Chitosan is highly molecular and is composed mainly of monomer linked D-glucosamine and acetyl-D-glucosamine. The ratio between D-glucosamine and N-acetyl-D-glucosamine is the degree of deacetylization, which is really important in terms of chitosan. The acylated units have typical degree of deacetylation between 70 to 95% and molecular weight, which varies between 10 to 1000. Furthermore, it is also a non-toxic, biodegradable and biocompatible polymer. Various studies have shown that chitosan possesses antimicrobial effect against bacteria, fungi, and viruses. The cationic amino group carried out by C2 position of glucosamine units of chitosan are responsible for the formation of polyelectrolyte complexes with the anionic group and different polyamine like carboxylic acids, alginate, xanthine, carrageenan, and carboxymethyl cellulose, pectin, and polylactic acid. So in terms of flexibility, chitosan can be converted into fiber, but it is costly. To cut the cost can be used by blending with other natural fibers and polymers. The blend of chitosan were reported with alginate, collagen, polyethylene dioxide, starch, silk, and polyvinyl alcohol. Due to its biocompatibility and natural antibacterial property, it has enormous application, not limited to filtration, packaging, and medical sector. Furthermore, global chitosan market size is expected to grow USD $8.4 billion by 2030 with a compound annual growth rate of 15%. Chitosan nanofibers have enormous application in filtration and packaging. To produce chitosan nanofibers, electrospinning is well-known methodology worldwide, which is being used to produce nanofibers from different polymers. So chitosan nanofibers can also be produced by electrospinning. So let's talk about electrospinning, which is an effective process to produce nanofibers by using synthetic polymers and natural polymers as well as ceramic and metals. This technology basically is a combination of electrospray and solution dry spinning. In the electrospinning process, high voltage is applied between the nail tip of the polymer containing a syringe and the collector, which induced charge in the polymer solution. Induced charge in the polymer solution enables the deformation of the spherical droplet shape of the polymer to a conical shape. Furthermore, when the electrostatic repulsion force value increases from the value of the polymer surface tension, a charged fine polymer jet ejects from the tailor cone and collected on the opposite pole of the electric field. During this, the traveling distance from the tip to collector enables the solvent to evaporate due to the bending and stretch of the polymer. According to the basic principle, electrospinning setup consists of three main parts. One, a high voltage source. The second, a syringe-based spindlet of the polymer feeding having a metallic needle tip, and a collector which should be grounded conductor. In the first step of operating the procedure, fill the polymer solution in the syringe onto the machine by providing basic machine setup like the volume of the solution, flow rate, syringe diameter. After these initial setup, high voltage is applied between the tip and syringe and the collector. So through this process, we can produce the nanofibers of the polymeric solution. So in this current study, we use the electrospinning process to produce chitosan nanofibers for the desired application. Now let's talk about the main objective of these studies. Our main objective was to produce the chitosan nanofibers with a smooth production of the chitosan nanofibers, beads-free formation of chitosan nanofiber. Secondly, to check the impact of the voltage on the chitosan nanofibers production process, and to check the impact of working distance on the resultant nanofibers. The fourth objective was impact of chitosan concentration on the resultant nanofibers, and lastly, obtain the maximum possible concentration of chitosan in resultant nanofibers to get the desired application in the field of filtration and packaging and medical application. In terms of methodology, we use chitosan as a main polymer, polyethylene oxide as a co-spinning agent, glacial acetic acid 50% was used as a solvent, electrospinning setup were used to produce nanofibers with the voltage ranges from 15 to 20 kV with the two working distance which were 10 centimeter and 15 centimeter. To analyze the efficacy of the process and the production of the nanofibers, we use SCM analysis, and the model of the SCM was TESCON Mirror 3 GMUVP Analytical FE SCM. In this section, we'll discuss the results and we'll discuss the key finding of the results as well. First of all, we tried the 1% solution of the chitosan to produce the nanofibers by using the co-spinning agent, and experimental results of 1% of chitosan nanofibers on two different working distance and high voltage are shown in this slide. All four samples showed smooth Carthusian nanofibers without beads. Sample 1 and sample N1 and N2, which were produced at 15 kV voltage while keeping the working distance at 15 centimeter and 10 centimeter respectively, while sample N3 and 4 were produced at 20 kV voltage while keeping the working distance at 15 centimeter and 10 centimeter respectively. And we concluded that 1% solution smoothly produced the Carthusian nanofiber. So we proceeded the experiment by enhancing the further concentration of Carthusian to check the impact of high concentration in terms of nanofiber production. In our next slide, similarly, we tried 2% Carthusian solution concentration, which also showed the smooth nanofiber production without beads free. Sample 5 and 6, which were produced at 15 kV voltage while keeping the working distance at 15 centimeter and 10 centimeter, while sample N7 and N8 were produced at 20 kV voltage while keeping the working distance at 15 centimeter and 10 centimeter respectively. And here we also see that the smooth nanofibers were produced by keeping the 2% Carthusian solution concentration. In terms of 3% Carthusian solution, same results happen all for samples with 3% Carthusian solution showed smooth nanofiber production without the beads. After that, at high concentration, in case of 4% and above, solution wastage was high and the electrospinning process was unsuccessful due to cohesive nature and high viscosity of the resultant Carthusian solution. Furthermore, the high concentration of the high concentration of the Carthusian increases the amount of strong hydrogen bonding between amine and hydroxyl groups of Carthusian molecules and hinders the flow of polymer solution, which yields the unspinable results. Therefore, we further optimize the experimental design and try to get the result on by using 3.5% of Carthusian concentration for spinability. And when we tried 3.5% Carthusian concentration of spinability, got successful results as shown in the form of sample N31 and N32. The smooth nanofibers produced, and these 3.5% were the maximum concentration of the Carthusian which we got by keeping the other process parameters constant. And these were used for further application of filtration and packaging material production. To summarize the results, when we see all these results in two graphs, the graph A shows that the impact of voltage at 10 centimeter and the graph B shows the impact of voltage at 15 centimeter. The trend is same. It means when we increase the voltage, the finer fiber produced, and red line shows that finer fiber produced in case of 20 kV voltage, and black line shows the as compared to the 20 kV coarser fiber diameter were produced by applying the 15 kV voltage. In general, long working distance promotes higher draft in the polymer jet during electrospinning. However, bending instability of the jet in the presence of an electric field is also very important in this phenomenon. Therefore, longer working distance accounts for higher whipping instability of the jet and is responsible for the reduction of diameter of resultant fiber due to acceleration and higher stretching before the fiber deposition on collector. As a result, fiber diameter reduces with the increase of working distance. Apart from the working distance, applied voltage, which I already explained, is also really important to study regarding nanofibers morphology. Results show that average fiber diameter of Carthusian nanofibers was also reduced with the increase of applied voltage from 15 kV to 20 kV while keeping the other process parameters and working distance constant. In conclusion, smooth nanofiber production were observed up to 3.5% Carthusian concentration by keeping the other variables constant. Solution with 4% and above Carthusian concentration could not produce nanofibers due to high viscosity and high surface tension of the solution. In terms of voltage and working distance, higher voltage and longer working distance develop finer diameter nanofibers in all the samples. For future work, needleless electrospinning process is taking attention of the researchers to further optimize the process for commercial viability. Another perspective of the future work is commercial viability of to produce nanofibers coated functional clothing for research and innovation and commercial production and commercial utilization of this process would be helpful for the future work. Thank you so much.
Okay, thank you, Dr. Tosif, for this informative talk. And now we would like to move to the last speaker of our conference, who is Hina Khadim. She is a PhD student in Interdisciplinary Research Center in Biomedical Materials, Comsat University, Islamabad. And she is going to talk about fabrication of novel chitosan-based thermosensitive hydrogels for effective antibacterial activity. Over to you, Ms. Hina.
Yes. Assalamu alaikum, everyone. Is my voice visible to everybody and my screen as well?
Yes, we can. Okay, we can see your screen also.
Okay. Okay, I'm Hina Hadim and I am here to present my paper here. And I'm the co-author of this paper. And with the consent of all other remaining authors, I'll present this work. The title of the paper is Fabrication of Thermosensitive Hydrogels for Effective Antibacterial Activity. And I'm from COMS Islamabad Lahore campus, working under the supervision of Professor Dr. Neela Asif at Interdisciplinary Research Center in Biomedical Materials. And my presentation will cover the following contents: introduction, methodology, characterizations, and conclusion. Let's move towards introduction first. I'll introduce biomaterials. Biomaterial is a substance that can be engineered to interact with biological systems for some specific medical purpose, following the process of tissue engineering. Tissue engineering is a field that uses a combination of cells, engineering, various methods and materials to restore and replace biological tissues. Biomaterial is used as prosthesis, means implants in various regions of the human body, such as joint and hip replacement, heart valve, and blood vessel prosthesis, is also as cochlear replacements, contact lenses, dental implants, and skin repair devices. There are various types of biomaterials that can be classified as based on polymers, ceramics, metals, semiconductor materials. Polymer-based biomaterials, they have applications in drug delivery, skin, cartilage implants. Ceramic-based biomaterials, they are used as bone replacements, dental implants. Semiconductors are used in sensing and biosensing application, while metal-based biomaterials, they are used as orthopedic replacements and dental implants. Next, we have hydrogel. Hydrogels are three-dimensional cross-linked polymeric structures. They have the ability to absorb and retain large amount of water because they have hydrophilic functional groups in them that are capable of holding wound exudate in them, and hence they promote moist healing. Moist healing is very much essential, and it is good as compared to dry healing, because in moist healing cells and tissues, they have more way for the migration as compared to dry healing. And hydrogels have applications in wound healing, drug delivery, cartilage filler, and biosensing. And moving towards my application, wound healing. Wound healing is the ability of the damaged tissue to repair itself. There are various types of wounds. Let's see. First one is first degree burn, and in first degree burn, the uppermost layer of the skin, that is epidermis, it ruptures. In second degree wound, dermis is affected, and in third degree wound, hypodermis and whole of the muscle, it gets damaged. Therefore, there is in such condition, there is an instant need to cover the wound area, and keeping in view the significance of such a wound, this area needs to be addressed. Now we have the methodology Here is the schematic route for the synthesis of chitosan-based polylysine hydrogels, and chitosan solution was prepared in HCl, followed by the addition of the active ingredient. Then beta glycerophosphate was prepared. Both the solutions, chitosan and beta glycerophosphate, they were kept on hot plate in ice bath to maintain the temperature. Beta glycerophosphate was then added dropwise to the chitosan solution, and then pH was noted. The mixture was then transferred onto water bath at 37 degrees Celsius, and gelation time was noted. This led to the formation of the hydrogel. On the basis of this mechanism, two distinct compositions of hydrogels have been synthesized. One is 15% and the other is chitosan-based polylysine, that is 20%. The difference is in the content of the active ingredient. Next, we have gelation time. In gelation time, we have determined the gelation time by inverted tube method. Hydrogel solution was shifted from 4 to 37 degree into a glass vial. Glass vial was tilted after every minute, and the flow of the hydrogel was observed by observing with the help of the naked eye. The gelation time was noted until the hydrogel stopped to flow. And in this hydrogel formation, glycerophosphate, it played a major role in the cross-linking. When it was added, glycerophosphate was added, it increased the hydrogen bonding and decreased electrostatic repulsion between the chitosan chains. Phosphate groups of beta glycerophosphate, they developed electrostatic interaction with the amino group of chitosan, and it enhanced the interchain hydrophobic interactions between chitosan polymer by interacting with hydrated water molecules of chitosan. And at low temperature, chitosan contained water of hydration due to the presence of hydrogen bonds between the hydroxyl groups of chitosan and highly polar water molecules. And when temperature was increased, the hydrogen bonds broke, and the rotational and the vibrational energies of the hydrated water molecules, they increased and led to the decreased ratio of hydrogen bond. These all factors favored the removal of hydrated water by glycerophosphate from chitosan chains easily. Thus, hydrophobic interactions of dewatered segments of chitosan dominated, led to the thermosensitive hydrogel formation. And then these hydrogels, they were their swelling ability, cytotoxicity, antibacterial, and hydrophilicity was analyzed. Swelling study is an important characteristic of hydrogels to be employed in wound healing. This study provides evidence of the absorption ability of the hydrogels that facilitates the healing process. And it was done in two media. One is water and the other one is PBS. The swelling ratio, here in table you can see the swelling ratio increased as the PL content increased due to the hydrophilic groups of the active ingredient. This is in case of water, and in case of PBS, the maximum percentage is lower. This is because as the hydrogel was dipped in PBS, the active ingredient, it released from the hydrogel and did not lead to as much increase in swelling ratio. Therefore, it has less percentage in PBS. Next, we have antibacterial study. Antibacterial activity is the most important characteristic of a biomaterial to be employed in wound healing to analyze the adequate protection against a microorganism and minimize the chance of infection. This antibacterial activity, it was performed against 3 bacteria, E. coli, Asorius, and MRSA, and that is methicillin resistant Staphylococcus aureus, and it was done by innovation zone method. All these bacterial strains, they were inoculated for 24 hours, and the optical density was it was settled till 0.1, and these aggregates were prepared, and it was streaked over to these plates, and samples were placed. After the placement of the sample, after 24 hours, these zones were measured in mm, and it has shown good zones against all 3 bacteria. And in case of MRSA is very resistant type of bacteria, and even with this, our active ingredient, it has shown a good zone of 14 and 14.5 mm. That means the drug is very much effective, as well as the drug is effective, as well as the composite is also very much effective against these bacteria. And this zone is because of both PL and CS chitosan. It has amino groups, and these positively charged amino groups, they bind with the negatively charged bacterial surface. They hinder the growth, decrease the synthesis of DNA, and cause cell death. And same mechanism is shown by poly-L lysine. They electrostatically bind with the surface of the bacterial membrane. The positive charge of the PL, it interacted with the negative charge of the lipopolysaccharides and proteins of bacterial cell membrane. The electrostatic interactions, when increased in number, the bacterial membrane structure got disturbed by the change in permeability of the bacterial membrane. These interactions, they interfere with essential nutrients to get inside the membrane to the cytoplasm. As a result, the bacterial membrane got fractured and bacterial cell damaged by PL. Then we have a contact angle measurement. Contact angle measurement provides information about the hydrophilicity of the hydrogel that is considered as the most suitable characteristic for the application. Large contact angle is considered suitable for the hydrogel application. Larger angle will lead to better adhesion of the hydrogel to our cells, to the affected area, and it leads to better migration and proliferation. A good angle is considered between 40 to 90, and our composite, it has shown the contact angle between it is 15% hydrogel. It has shown contact angle of 57.2, and the other with 20% hydrogel containing the active ingredient, it has shown contact angle of 56. And the last, we have a migration assay that tells us about the cytotoxicity of our sample. This assay was done with mouse fibroblast cells, and a scratch was made into the well, followed by the removal of the remaining cells, and media was added. After 24 hours, the gap was filled with the cells. This means that the cells have our media, it has promoted proliferation, and it has got attached. The cells increase in number, and they have moved and covered the remaining area. In the conclusion, I would like to add that hydrogels were successfully synthesized that promoted wound healing through the structure and loaded active ingredient. Hydrogels, they have demonstrated a maximum swelling of 23.5%, and they have revealed good antibacterial efficiency against the resistant bacterial strains. The contact angle results, they have demonstrated hydrophilicity of the synthesized hydrogels, and migration assays, they have demonstrated that migration and proliferation potential of the hydrogels, and they have supported the non-toxic behavior in the wound healing process. And at the end, I would like to add about the testing services that are available at IRCBM. These all characterization facilities are available at our research center, IRCBM. Our center is equipped with many state-of-the-art instruments, and all these facilities are available. If somebody wants to get his or her samples tested, you can get them tested by contacting directly. The contact is given, or also by HEC testing services portal. I acknowledge my professor Anila Asif, my supervisor, the whole IRCBM team, and my department of chemistry. Thank you so much for your attention.
Okay. Thank you so much, Ms. Hina Kadim. It was very informative talk, and that was, I will check question answer. So we don't have any question. So it was the last talk for session 3. So we will have now a short break, and then we will join back at 4 o'clock Pakistani time for closing session of second international conference on polymers and composite. Thank you. Stay tuned.